All right, let's kick off. Okay, people can join. Welcome, everyone. Thank you for joining us for the Rail Industry webinar, Shaping the Future of Rail, Metrology and Innovation. Today, we will take a look at metrology's role in rail manufacturing. My name is Kevin Warwick, and I am the Director at Scan-Xpress. Before I give you a little background about Scan-Xpress and the 3D measurement solutions we offer, I would like to introduce our speakers today and outline today's agenda. First up will be Tamara Collenberg from the Department of Transport and Planning, who will give us an overview of Victorian rail manufacturing. Secondly, I will present some information outlining the importance of metrology in rail manufacturing. Then, Ben Singer, our lead metrologist, will take a closer look at some specific applications in the rail industry and take a deeper dive into the metrology tools available. Finally, we will close with a Q&A session. So let's start with a little background of Scan-Xpress. We're a family-owned business established in 1997, focusing on precision 3D measurement for inspection and reverse engineering. Our key technology partner has been Zeiss since 1999. We offer metrology products in both Australia and New Zealand and metrology services anywhere in the world. Our headquarters is in Melbourne, branch office in New South Wales, technical partnerships in both Queensland and Adelaide. We are an experienced team with an extensive range of metrology tools, over a dozen advanced 3D measurement systems. With 7 engineers servicing sectors such as power gen, aerospace, defence, medtech, and of course rail, we can support your needs anywhere in Australia and New Zealand. And rail is why we are here today, and specifically Tamara Collenberg. Thank you for giving us our time today, Tamara. I now invite you to speak.
Thank you, Kevin. Thank you to Scan-Xpress for inviting me today. So for almost 30 years, Scan-Xpress has been delivering advanced metrology, image correlation, and quality inspection across Australia and New Zealand, and applying that expertise to improve how we design, build, and maintain transport systems. What stands out most in their passion for homegrown engineering, is their passion for homegrown engineering, working with our universities, collaborating with major local manufacturers across rolling stock, medtech, automotive, and aerospace. They show us exactly the kind of innovation ecosystem we want to foster here in Victoria. As Victorian rail advocate, my job is to be the voice of industry, to work with government on strategies that keep our sector competitive, sustainable, and ready for the future. Today, I want to step back from the day-to-day and share a broader picture of where the Victorian rail manufacturing stands, how it's grown, and what will keep us ahead. Victoria's population is growing fast, and rail is at the heart of keeping the state moving. We design, build, and maintain our trams, and buses here at home in Victoria. That supports thousands of skills jobs, from component supplier to assembly and maintenance, and it gives us a fully integrated world-class rolling stock industry. Keeping that capability matters. Once the skills, facilities, and know-how leave, they're really hard to bring back. That's why a steady pipeline of investment is not just about the vehicles we see on the tracks, it's also about preserving sovereign capabilities and building a resilient local industry. Over the past decade, rolling stock manufacturing has been one of Victoria's biggest industry success story. We have deliberately built a steady pipeline of orders, 100 next-generation trams, 25 Extrapolis 2.0 trains, and continuing the program of Velocity regional trains. This gives industry the certainty it needs to invest in its people, its facilities, and in innovation. That approach has delivered some of the highest local content level in the country, with 65% local content for the next generation trains and 60% for the Extrapolis 2.0 trains. It has created long-term careers opportunity, especially in maintenance, work that is critical to safety, efficiency, and extending the life of our assets. And it has attracted a more diverse workforce, bringing in more women, more young people, and more workers from underrepresented backgrounds. We are now entering a period of technology called transition. Lower emissions fleets, more digitalized operation, advanced materials, and predictive maintenance will be the new normal. For Victoria to stay ahead, our industry needs to be competitive on the global stage, ready to invest in its workforce and able to deliver the innovation that the future fleets will require. The role of government is to set the right condition for success, but delivery always happens in partnership with the industry. We are building stronger skills and education pathways, from school programs to advanced apprenticeships, and creating opportunity for experienced workers to be retained and reskilled. We are working with other government agencies to refine our local content requirements so they will genuinely build capability rather than simply meeting compliance targets. We will begin rolling this out as new contracts are awarded. We have a particular focus on attracting and developing skills and providing export opportunities. We work with companies to explore export markets and adopt advanced manufacturing techniques so our products are competitive globally and unique enough to attract further investment. Importantly, our procurement model looks at the entire life of a project, from design and build right through decades of maintenance. That way, the economic and skills benefit of every investment are sustained over long term, not just during the production phase. When government and industry work together, it fosters capability, innovation, and future direction, and we create a certainty and a momentum that benefits everyone in the sector. So my message today is this: Victoria's rail manufacturing sector is strong and it's growing, but its future strengths will come from collaboration. We have a decade-long track record of working with industry to deliver jobs, skills, and advanced manufacturing capability. Now, we must extend that partnership into the next generation of rail manufacturing, one that is greener, more digital, more globally competitive, and more inclusive. If we each do our part, investing in people, in capability, and in innovation, then Victoria will not just remain the home of rail manufacturing in Australia, it will be the place where others look to for leadership. Thank you very much.
Thanks very much, Tamara. It looks like there's lots of opportunity for businesses working in the sector. I'd now like to just take a bit of a time just to basically elaborate on why metrology matters in the rail manufacturing industry. Okay, I'd like now to take a couple of minutes to sharing why metrology, the science of measurement, is critical in rail manufacturing, and how Scan-Xpress, together with Zeiss technology, supports this industry with world-class precision and quality assurance. Metrology in rail. In rail manufacturing, every component from wheels and axles to car bodies and bogies must meet extremely tight tolerances. Even minor deviations can cause vibration, noise, excessive wear, or in the worst case, safety risks. That's why metrology isn't just about inspection, it's about ensuring quality, reliability, and long-term performance across the rail network. Where metrology adds value. Metrology touches every stage of the rail value chain. It starts with verifying raw materials, continues with in-process checks to prevent defects early, and ends with final inspection before components leave the factory. Even in maintenance, metrology supports reverse engineering of worn parts to extend the life of assets. Scan-Xpress capabilities. Scan-Xpress has nearly 3 decades of experience in precision measurement. We specialize in non-contact optical 3D metrology, ideal for large, complex rail components. We provide a full range of services, measurement, inspection, reverse engineering, and training. Our role is to help manufacturers improve quality, speed up production, and reduce costly errors. Our Brunswick headquarters has more than a dozen different 3D measurement systems, ranging from handheld scanners, structured light scanners, laser trackers, terrestrial systems, and our recently implemented, fully automated Zeiss Scanbox Series 5, capable of measuring objects up to 2 meters in a fully automated fashion. This system is truly state-of-the-art and is available for service work as well as demonstrations. I invite you to come down and take a look. Zeiss technology. As a Zeiss partner, Scan-Xpress delivers world-class technology backed by one of the most trusted names in precision. Zeiss systems provide unmatched accuracy, reliability, and speed, perfectly suited to the demands of the rail manufacturing. Together, will bring together our global technology with local expertise and support. In closing, to summarize, metrology matters because precision equals safety, efficiency, and reliability in rail. At Scan-Xpress with Zeiss technology, we ensure manufacturers have the confidence that every component meets the highest standards. That's why metrology is not just measurement, it's the foundation of the rail quality. And now I invite Benjamin to take a closer look at some application examples specific to the rail industry. Thanks, Ben.
Yeah, excellent. Thank you, Kevin and Tamara. So effectively what I'm going to do now is go through some of the different technologies that we offer at Scan-Xpress. We've kind of got 4 different technologies that we'll look at. I've got examples of each of those that we can have a look at with real life examples and real life data. I'm also really keen on answering any questions. So as I go, please put any questions in the chat window, and there'll be a time at the end where we can go through those, and either myself, Kevin, or some of the other team will be able to go through those questions. So so please, anything that comes up, just pop it in the chat window. But just to quickly summarize who we are at Scan-Xpress. So we offer 2 different accesses to all of this technology. So we're both a sales company as well as a service company. So that means we can sell and install the systems into your companies. We also offer full training and support for those systems ongoing for the lifetime of those systems. But we also offer project-based metrology support. Now that can either be on-site or off-site. So you can send components to our main office here in Brunswick or our regional offices around the country. But all of our equipment is also mobile, so we can come on site to where the equipment is needed and perform the measurements there. We offer a full range of services, including inspection, reverse engineering, and data capture. So these are kind of the main different systems that we'll be looking at today. So 3D scanning, which kind of comes in 2 different forms, the handheld scanning and the structured light. Then we'll look at some terrestrial and some laser tracking as well. But where 3D scanning really comes into it is with, capturing full field data on really any component of really quite a varied size. Now these are usually for kind of 2 different applications. The first being reverse engineering, where we're creating drawings or CAD models from that captured data. And the other one will be quality inspection, where we're capturing that data for various forms of inspection. So that could be dimensional checks, checking new manufactured parts to make sure that they fulfill the tolerances. It could be looking at, identifying wear or damage on worn components, kind of a more of a maintenance application. So the first system we'll look at is our handheld scanner. So this is a handheld laser scanner, captures really nice, good quality data, and is really mobile and is really, widely used for lots of different applications in the rail industry. So first of all, I'll look at a little video that we actually shot one of our partners quite recently, and then we'll go into some of the live examples within some scan data. So let's have a look at this video to start with. Excellent. So that was like a nice quick overview on how the system is actually used in the field. Now, the great things about these kind of handheld scanning systems is their speed of capture and their portability, but also their ease of use. So it is really as simple as just picking up the sensor, plugging in the USB cable, and then within a couple of buttons, we're away and scanning. Now, the T-Scan Hawk, the system that the Zeiss manufacture, utilizes these 4 buttons on the back of the unit, and basically we can run through the whole scanning operation from just these 4 buttons. So what that means is when you're out in the field, maybe on board a train or a tram, or in the middle of a bogie or something like that, we can complete the whole scanning operation without touching the laptop at any point. So it really does make that process very simple. And this is how these systems are come. So basically, you've got the black carry case there, and everything is contained within that carry case. And essentially, we just need that and a laptop, and we're away and scanning. So what that means is we can take this out into remote areas and capture some really good quality data. So let's look at a couple of applications for this system. So I'm just going to dive into the software, and we'll have a look at some of the live projects. So the first one I want to look at is this one here. So this is a scan of some rails, and actually taking this out onto site and into the field. So what we can see is the system T-Scan Hawk that we were talking about, and this is the setup right here. So like I say, we've got the carry case, the laptop, the sensors all plugged into that, and this is actually running from a battery pack. So it means that we can be in those remote areas. Now the system uses reference points to basically locate itself around the area. So these reference points are necessary, and you can see those placed in these little magnetic spheres. So what that means is that the setup is really simple. We just place these around the area that we want to scan, and then we go ahead and capture our data. Now, the application for this was looking at are both paths aligned to the center. So effectively what we're doing is creating a geometry on all of the features that we're looking at, and in this case, looking at parallelism between the two. We've got the tolerance, in this case 5 mil. We're inside that tolerance, but we can also see the color map deviation of where that rail sits. So that's the left-hand side and the right-hand side. So there's a slight deviation from high, which is on the red, to low, which is on the blue, but all well within the tolerance. So nice, quick, clear results captured within a couple of minutes and inspected on. So the other example is a partial scan of a bogie frame. Again, scanned with the T-Scan Hawk. So again, you can see the reference points that we've placed on these magnetic spheres to make the setup really easy. We've just placed those everywhere, scanning that with the T-Scan Hawk. And this is the captured scan data. So the gray is the live scan data that we've captured on this, all captured within a couple of minutes. Now, the application for this was actually looking at weld analysis and deformation on the side of the bogie frame. So we're actually analyzing the live weld analysis back to national and international standards. So I think this is the ISO 502 standard for this weld here. So it's cutting loads of sections all through that weld and then doing various checks. So this is looking at one single section and some of the checks that are that it's calculating on that individual weld section. So then we're doing the weld analysis, but this is also doing the deformation of the side of the frame. So this is similar to what we were doing on the rail in the previous example, but this time we're looking at a flatness check across that whole side of the bogie. So we're fitting a plane to the scan data, inspecting this against quite a loose tolerance, that 10 mil tolerance. We've got a deviation value of 5.5 mil, and again we can see the color representation of that. So blue means the data is low; it's below that set plane. And then, the yellow and red means the data is high. So we can see it's actually bulging out right in the middle of the bogie there. So yeah, again, really quick data capture and clear and well-defined results for the inspection. So yeah, let's now move on to the second type of 3D scanning system that we're looking at, and what we call this is 3D structured light. So effectively, these systems are using a central blue light projector and 2 cameras on either side. Now, these come in various different shapes and sizes. You can see 2 different scanners on the screen here, the Atos Q in the top right, and then the bottom and the left-hand side are what was known as the Atos 5. So 2 slightly different versions of a scanner, but basically the same type of technology. Now, the advantage of these scanners is they capture higher resolution data, so smaller point spacing, so we can capture smaller features on components, but also to greater accuracies. So these systems are really more used for, precision inspection and, first article inspection, or looking at wear deviations and those kind of things on used components. So a lot more of inspection functionality to tighter tolerances than what we just saw with the handheld scanner. Now, these systems are really well used in industrial applications, and specifically for those inspection functions. They are still mobile, so we can still operate them in the field, as you can see here, on tripods or on studio stands, but not quite as mobile as you're going to get with the handheld scanner. So one of the limitations for these systems is you're not going to use them outside in those kind of environments where we're actually out on the tracks. That would certainly be an application for a handheld scanner. These are more kind of in the workshop or in a metrology environment. So let's have a look at one of an application for these kind of systems. So first, we've got a complete bogey frame. So this was scanned with a structured light scanner, and the application for this was actually reverse engineering. So we're capturing this data to be able to produce the CAD model to then remanufacture these or use that as a base for inspection. So this is the kind of data that we capture with our structured light systems. So as you can see, it's slightly higher resolution, full field scan data, and we're getting every point on the surface, as well as some of the data on the insides where we can see through the kind of inspection windows and that are cut into the bogey frame here. Now the inspection report for this looks something like this, where we're looking at full 3D inspection. So this is inspecting every point on the captured scan data against that of the generated CAD model. So this is kind of verifying, how well that CAD model has been designed. So everything that's yellow or red, again, means the data is high and it's above the CAD model. Everything blue means it's low and it's below the CAD model. So we can look at all the different surfaces where they fall. We've got a tolerance legend. So if things fall outside of a set tolerance, but then we can also start cutting sections through our scan data and looking at, the material thickness and things like that. So yeah, quite an in-depth version of the inspection. You can do an awful lot with it. So these systems kind of come in different shapes and sizes. So how we're kind of often using them is either in a manual or a semi-automated form. So the manual would be like the images you saw earlier with the system on a studio stand or a tripod, where we're physically moving them around the object. And the semi-automated is where we operate them with rotation tables, so we can kind of speed up that scanning process. But we can also fully automate this inspection as well. And that looks, something like this. Again, these come in lots of different shapes and sizes, but this is really for looking for, fast throughput of inspection, where we're trying to reduce that data capture time as much as possible, and where we're measuring parts in the tens or in the hundreds, and we want to kind of produce this in line in process. And yeah, let's have a look at a video and see kind of how that would look. So that system you just saw there was what we refer to as the Atos Scanbox 4 series. Now that 4 series can take parts up to about 800 millimeters in diameter. But let's have a bit of a closer look at that actually inside the software. So right here. So, a kind of perfect application for that would be something like, an axle box, where we're looking at precision inspection on some of the tighter tolerance features on this, but we also want to get the scanning complete in the fastest time possible. So as you can see, this is the scanner right here on the end of our industrial robot. This is utilizing a rotation table, and like you can see, there's not a huge amount of infrastructure around the scanner, so this can certainly be placed next to a production line with maybe a pick and place robot to load and unload our parts for us. Now, you might notice that this is exactly the same software that we were using with the handheld scanner and the inspection for that. So Zeiss produced one single piece of software, which is called Zeiss Inspect, and that works with all of the different scanning systems and controls the data capture as well as the inspection. So everything we do is in this one piece of software. Now, what we need to do for this part is program the robot. Now we do that for the first part, and then once that program's generated, then it's ready for every for the lifetime of this project. Now we can control the robot within the software by utilizing the controls right here, but we can also program it automatically from a CAD model. So if we press the Smart Teach button right here, this is going to generate the robot programming automatically. So the system is going to analyze the CAD model, and it's going to then position the sensor in the best place to capture as much of that data as possible. Now, the system works with a measuring volume, which you can kind of see is the white wireframe just in front of the sensor itself. So this is using a 500 mil measuring volume. So it's effectively a 500 mil cube, and we're capturing all the data within that cube. So the system has now created all of the measurement positions for capturing this part. And we can actually run through that process here and capture the simulated data, which you can see in gray is being built up over the top of the scan data. So we can see that this is actually going to take 1 minute 56, so just under 2 minutes to fully capture this entire part. And then, this is a full program ready to run. So if I had the scan box here next to me, I'd be able to, run this program on the scan box and start capturing data straight away. But one thing with this is most of the time, we're probably not actually interested in the whole of the part. We're probably just interested in that center bore, because that's going to be the most critical feature, especially if we're looking at something like a maintenance kind of application where these systems have been manufactured, they've been run, and we just want to check if they're still in tolerance. So for those kind of applications, all we need is that central bore. So what we can do is position the sensor in a way that we can actually capture that. Now I can see the live camera view over here. So what we can do is position the sensor so I can see all inside that center bore, something a bit like that. And let me just strain it up so it's a little bit better. So we can take one scan. That's going to generate that scan data there. See, I'm missing a little bit there. So let's move them in a little bit closer. And then I'll just override that measurement. So make sure we capture that. And then what we can do is actually copy and rotate that measurement around the axis for that central cylinder. So all we just do is select that one, go to automation, copy and rotate around the x-axis of our coordinate system. And let's say we want to take 7 measurements, including the first one. So then we got 8 rotations all the way around. Okay, so that's going to create that really nice, simple program just to inspect that central bore. Now, if we run that program, we've gone down from 2-minute measuring time to now a 30-second measuring time. So we can measure one of these parts every 30 seconds and produce our inspection report. So yeah, really nice and easy. The software interface is absolutely phenomenal for these kind of systems. So very easy to just set up these kind of programs and run them and capture some scan data. So yeah, let's have a look at actually something like that in operation live. So these 2 systems are operating in Europe, measuring bogey frames. The one on the left is sped up 5 times, so that's why the robots are moving significantly faster. The one on the left is in real time. But these are live applications. These are currently being used in the industry to measure, as you can see there, bogey frames and spring arms and all sorts of different rail applications. So these kind of systems are slightly larger than the 4 series that I was just showcasing within the software. So they can take parts actually up to 8 meters in length. And on the one on the left, you can see it's on like a rolling frame. So basically the parts can be loaded up outside of the scan box, and they can just be rolled in, inspected, and then rolled out the other side. So it's definitely a fully inline process. So yeah, that's kind of an overview on 3D scanning, both handheld and structured light. Let's move on to some other laser technology now. I'll just remind you, please, any questions, if anything I've forgotten, please pop it in the chat and we'll jump back into it at the end. But yeah, next one is going to be terrestrial laser scanning. So terrestrial laser scanning is a method of capturing huge amounts of data in kind of a single shot, a single setup. So it utilizes a laser that basically rotates vertically 360 degrees, but also horizontally 360 degrees to capture a complete environment in that single setup. There's lots of different applications for this in the rail industry. So things that this could be used for, capturing full vehicles. Now that could be for inspection. It could also be for retrofitting. So potentially if we're looking at, remodeling insides or outsides of full vehicles, then this is the kind of technology that can capture all of that data very, very quickly, but also for infrastructure. So mapping full stations or, actual, structural infrastructure. So these kind of systems can measure, measuring volumes up to hundreds of meters. So effectively, we set up this tripod like you can see here, and this is going to capture that complete environment within, a minute or two. And then we can tile these together to capture, large areas of data. Now, in terms of kind of raw accuracies, these certainly aren't going to hit the same kind of levels that we do with the handheld scanner or the structured light scanner. So these wouldn't be used for kind of that precision inspection, more for kind of generating full point clouds of environments that we can then use for reverse engineering, designing things around those kind of applications. So again, let's have a look at a quick video showing these kind of systems in action. Excellent. So yeah, the video probably didn't quite do it justice with the amount of detail that we can capture with these kind of systems. So, the data looks fantastic and can really be really valuable in capturing those really large areas. So the last kind of system that we'll be looking at today is the laser tracker. So laser tracker, uses laser technology like the terrestrial scanner, but rather than capturing full areas, this is a point measuring device. So effectively, the operator will be holding a reflector or a receiver. The system will set up on a tripod, and it captures a single point distance to that receiver. So this is kind of how they look out being utilized, for applications. Now, these certainly are an inspection tool. They are very accurate, especially over large distances. And one of the really advantages of these systems is their speed of capture. So being able to capture a point, being able to inspect it, make adjustments to it if necessary, and then re-inspect it. So yeah, this is one of the systems that we're utilizing. And as you can see here, from an accuracy point of view, we're looking at 16 micron accuracy for the setup. But the important thing is the accuracy per meter. So it's actually only adding a 0.8 of a micron, 0.8 of a micron deviation per meter of scanning. Now, what that means is we can scan really large areas, large volumes, and not have a big decrease in the precision of the system. So the system that we're using currently, which is this one here, you can see a 35-meter measuring radius in a single setup. So what that means is we can measure distances up to 70 meters in a single setup without moving the system. Now, if we wanted to measure larger than that, then we could use tracking nests and things like that to be able to leapfrog around and measure larger areas if necessary. Now, one of the really key applications for this one currently is measuring jigs and fixtures for the rail industry. And like I say, the advantage of that is being able to take a measurement, adjust the feature, and then remeasure it. So, with these jigs and fixtures, you've got hundreds, maybe thousands of individual faces that need to be shimmed and properly calibrated. And the ability to set datum planes and then measure, to make sure that all of those faces are flat, adjust them, reshim them on the fly is really, really valuable. And then, being able to make those quick adjustments and have that full field inspection report at the end to be able to validate all of those features. So that's the laser tracker. And so that's kind of the all the technology that I wanted to discuss. So please, any questions for myself? Hopefully tomorrow. Kevin's certainly still here, so any questions to any of us, please pop them in the chat. While we're waiting, Kevin, have you got any questions?
No, but I mean, the rail industry, that's a good overview. Thanks, Ben, because, I think as you showcased, there's quite a lot of different variations in measurement technologies, from structured light to laser to terrestrial, and the accuracy of the laser tracker over long distances is phenomenal. And as you know, we support quite a lot of the rail industry at the present, and just want to make sure that everyone who's attended is aware that these options are around today, are viable. We're an experienced team, and while we have our headquarters in Melbourne, we're also traveling constantly all around Australia and New Zealand, and sometimes even internationally. So if you'd like to reach out at some stage and talk specifically about some of the needs that you potentially have, we'd be really interested in getting to know your issues a little bit better. I don't see any questions in the chat. Thanks, Tamara, for your time.
Excellent. So we've got a question there. Can the scanners be used on drones on the dynamic, not stationary conditions? Yeah, great question. Kevin, do you want to take that, or you want me to?
You go. Yep.
Yeah. So some of them certainly can. The scanners that are utilized probably are not best suited for kind of applications on drones. But one of the systems is photogrammetry. Now that's not really something that I covered today. It was discussed, and maybe I should have included it. But essentially, photogrammetry is taking measurements, but just from images, so just from static, images just from a DSLR camera. Now we utilize those kind of systems. They're produced by Zeiss called Tritop, and we utilize that in the rail industry quite a lot. But that can certainly be applied to drones as well. The 3D scanners and the terrestrial scanners that I kind of showcase in my presentation need a little bit more stability than you're going to get from a drone. So that's probably why it's probably not the best kind of technology, but photogrammetry certainly is. And I know that can be utilized for capturing like large scale, sections of tracks. So yeah, excellent question that.
Thanks, Ben.
So yeah, do the Zeiss scanners suffer from blind spots, deep recesses caused by camera capture? Again, Kevin, do you want to go? Or you want me to go?
Yeah, well, look, simply put, yes, it is a line of sight, and because we do have twin cameras, it actually operates as an advantage. Early generations of the systems required that both the left camera and the right camera saw the same surface before it could capture accurate data. I guess the evolution of these systems has meant that the whole cameras can actually work, or the two cameras can actually work independently of each other. The marketing term that Zeiss uses is triple scan, because it can take a scan from the left camera, scan from the right camera, and then a scan both combined. So, but still, even with that, the deeper the recess that you're trying to project the light pattern into, the more challenging it becomes. Essentially, there's a ratio of about 3 times the diameter is the depth that you can actually capture. However, the systems can be combined with optically tracked touch probes. So when the projected light that the camera needs to see hitting a surface for it to create any Cartesian coordinates, if that's not possible, then a T-scan or a T-probe with a cluster of points at the camera, so the same points that we're using to orientate the system relative to the part, is then placed onto a handheld T-probe, and you can have an extension of 500, a meter if you need, to then probe the surfaces that you can't actually get the projected light onto. So yeah, yes, it's true, they are line of sight restricted, but there is ways to overcome that. Even undercuts are possible. Just wait for a couple more minutes maybe to see if there's any further questions.
Yeah, we will absolutely make a copy of the recording available. So you should get a link to that in the email.
Terrific.
Yeah.
Maybe we should wrap things up then.
Yeah, excellent. I mean, if anything comes up, if you think of any other questions that you kind of wish you'd asked, just please let us know. You can reach out via email. There is just one that's come into the application for integrated automation by the in-process checks. Kevin, do you want to?
This is your turn.
Sure. Yeah, absolutely. So there are lots of examples of those kind of automated scanning systems being integrated into production lines. To be honest, not a huge amount over here in Australia. We do have automation systems in industry, but actually having them, integrated into the production line isn't something that Australian companies have done yet. But we are in discussions with customers about that kind of process. But yeah, yeah, Kevin, do you want to?
No, it's a fair point. What we've actually experienced so far is really sort of batch sampling of production parts that are taking off into an environment. The examples that we showcased were more open. There was no enclosure, but the systems we have installed in Australia and New Zealand are more configured as the marketing term is a scan box, and they literally are a box. The bigger the box, the bigger the parts that you can scan. So they really sort of are removed from the production line and then taken into an environment where the metrology is performed. However, the variations on the system, such as the modular unit that was showcased earlier in the Series 4, does lend itself to a pick and place or a conveyor belt where the system can actually access the parts. You've got issues like flipping the part if you want to measure the underside of that, and these are some of the integration of the pick and place robots. We are having conversations, but we don't have any installations for inline inspection at the moment. As I mentioned, though, we do have a Series 5 scan box in our Brunswick facility. So if you're ever in Melbourne, we're dying to show it off. We've had it for the best part of a couple of years so far. We're using it for the provision of service work in larger volumes, but also for, if you have a part that's under 2 meters in size, then it's something that can be sent to us and we can develop an inspection report and show you how it might actually work for your application. Well, with that in mind, I'd like to thank Tamara for joining us today, Benjamin for putting together a terrific presentation on the varieties of scanning solutions that are on offer. Aman and Lee part of the team to actually put the webinar together, and everyone that attended, thanks for your time, and please don't hesitate to reach out. Ben, would you like to say anything in conclusion?
Yeah, no, thank you very much. And like Kevin says, yeah, any other questions that come up, please reach out, and yeah, we'll, look forward to hearing from you.
Terrific. Thanks, everyone.
Cheers.